Today we're talking about Hardy-Weinberg equilibrium. This principle states that genetic frequency or allele frequency will remain constant in a population from one generation to the next. We are going to take a close look at the Sour Patch Kid population. This population is currently in Hardy-Weinberg equilibrium. You can see that this bag is the whole world of Sour Patch Kids. This means that there is an infinitely large population possible. I'm going to make sure to shake up this bag and have random mating occur. Now, inside the bag are 3 genotypes of the allele for skin color for the Sour Patch Kids: AA red, AC yellow, or CC blue. And all genotypes are equally fit, meaning that they can survive equally within this environment. Now, this population is bound, which means that there's no migration possible. There's nobody getting in or out. And lastly, there are no mutations present. All of these factors combined will create the Hardy-Weinberg equilibrium in this population. While in this equilibrium, genotypic frequencies can be expressed as P squared AA plus 2PQ AC plus Q squared CC, where P and Q are the frequencies of the big A and C alleles, respectively. First, we're going to start off with how many we have in the total population. All the fitness is 1 because they'll equally fit. Now, to find the frequency, we're going to divide each by the total population. That is going to get our percentage of each genotype. Now, to find the allele frequency, we'll plug it into this equation here. You can see that in this AA, there's 2 A alleles. That's why we're going to multiply this number by 2. And here there's only 1 A allele. That's why we're not multiplying it by 2. We're just adding that number. We're going to divide it by total number of alleles, which is total number times 2. And you will get the P and the Q. Now, P plus Q will always equal 1. And that's what we're seeing here. When we plug this in, we get our gametic array, and we get our genotypic array. What if I told you selection was taking place in this population? The humans are predators to the Sour Patch Kids. They love to eat the blue, they like the yellow, and they leave the red. By the end of the bag, there's always red left over, no blue, and just a couple straggling yellow. This is altering the fitness of the Sour Patch Kids by the genotype and will affect the survival rate. This is an example of directional selection because as there are more A alleles, the fitness of the genotype increases. This process of selection is violating the Hardy-Weinberg equilibrium. We want to see what proportion of our original frequencies have survived. Looking at the fitness, we can see the 2 A's have the highest fitness while the C's are the most eaten. Now we have the adjusted survivors by multiplying these two numbers together. This does not equal 1 like it must in Hardy-Weinberg equilibrium. We're going to balance that out by summing all of these numbers up to get our average fitness. Then we're going to divide our adjusted survivors by the average fitness to get our relative genotypic frequency after selection. This brings our formula back to equaling 1. Now, if we wanted to find the allele frequencies, we simply take the allele frequency for AA times half of the frequency of AC, and that is our new P, and this is our new Q. Here we have our gametic array, P plus Q equals 1, and that is sure the case here. So good. You want one?